Talking about the least action nuclear process theory of cold fusion. It's a model that's based entirely in classical physics. Very good. I'll be talking about the process energy, where it comes from, and where it's stored. We'll also be talking about transmutations, the kinds that occur in these in the nuclear reactions in our electrodes, and how those are ordered in how the order is determined. And then we'll talk about the model calibration results. Can I move? Yes, okay. The source of the energy in this model is the kinetic energy where can I get the, there we go. The kinetic energy of protons outside of our nickel electrode. And when the proton is absorbed into the nickel electrode, it's quieted. Its kinetic energy goes to zero, and the first law of thermodynamics tells us that that energy does not just go away, it has to go someplace. So I'm going to put it back into the lattice, nickel lattice structure. And that has its own consequences, which we see here. I've calculated the number of atomic layers that are required for a deuterium fusion using the kinetic energy of a 0.2 centimeter per second proton. And you can see, it's only 100 atomic layers. David Kidwell saw this when I first presented it, and he said, no way, that's silly. He called me up 2 weeks later and he says, you're right. You are so right. There's a capacity for an enormous amount of fusion energy in the electrode. So the energy is harvested from the environment, and it causes the internal energy in the electrode to continually rise. And this is rising throughout the entire experiment until the moment of the first reaction. And that is the first step of the two-step fusion or two-step transmutation process. So we have either a stable or an unstable isotope at this point. If it's unstable, it goes through a second step called an LAMP decay, where it decays down the normal pathways. There's nothing new here, okay? I'm not doing any magic, okay? But the one that is selected is this pathway that results in the lowest or the smallest mass energy change. So it makes it deterministic. Beyond the LAMP decay, there is rare isotope decay. These are theoretically possible, but they don't occur in nature. And nuclear fission of substances that are theoretically capable of spontaneous fission, but don't necessarily do it in nature. So what is the least action process? First of all, it's a nuclear process, so it produces a work product. And every step in it is determined by the principle of least action, a principle that goes way back in the history of physics, back into the 19th century. And what it does is it says the selection is based on the process that, or the step that results in the smallest mass energy change. For example, we can take our example here of a nickel 58, silver 107, plus one neutron. We get rhenium 166. And that decays down myriad pathways to 2, 3, 4, 5, 6 stable isotopes. Which one is it that the LAMP process finds? Going back. There we are. There can be only one least action pathway, and in this case it's to dysprosium 162. This is the least action pathway. The only elements of this that are operative are the initial and the final states. None of the intermediate states exist. This is 19th century physics, but it is the fundamentals of the physics that we all know. So it's the least action path. It determines the process in an absolutely deterministic way. In other words, it's selecting at every step, at every decay, there is only one step. And this is the hallmark, really, of classical physics, absolute determinism. So how is the cold fusion's energy stored? The energy is localized in this model between covalent nuclei, where a single gamma energy photon is resonant between adjacent nuclei. Okay? And the localization principle I'm going to use is Mossbauer resonance. And Rudolf Mossbauer discovered in 1957, this was his doctoral thesis, what's called recoilless nuclear resonant fluorescence. What he did is he used a gamma emitter to, okay. He used a gamma emitter to irradiate indium-191 nucleus, and what he found is that the emitted photon, gamma photon, was identically the same as the absorbed. And this won him the 1961 Nobel Prize in Physics. He had discovered a reversible thermodynamic process in nature. And what that means is that there is no energy change and no entropy change in this process of the back and forth here. We're going to advance Mossbauer's idea a little bit farther to energy storage, and we're going to replace his emitter with a nucleus that emits a gamma photon, and his detector with a nucleus, an identical nucleus, that absorbs the gamma photon and then emits it, where it is absorbed without any change in its energy or entropy by the first nuclei, and so on and so forth, if we can do that somehow. So what there are consequences to this because the nuclei are now located one wavelength apart. Okay? And as the proton loading of the cathode continues, its internal energy is continually increasing, which is what I showed you in the earlier slide, where you saw the energy rising and the nuclei becoming, well, the energy is rising and then we get fusion. The loading increases the gamma intensity, in other words, the gamma energy, the gamma photon energy, and this has some profound consequences. Remember, these nuclei are one wavelength apart, and over here we're looking at the energy increase. And as the energy increases, they become closer and closer together. Until ignition. We have our first fusion reaction. As the energy in the cathode continues to rise, we are going to get additional fusion reactions when their threshold energy is approached. Well, how well does a model like this work? I've used it to match the published data of George Miley, who did a wonderful experiment with a Patterson cell where he measured initial and final isotopes. Will the model be good enough to tell us something about new isotope appearance, maybe the order of isotope appearance? Excess heat? Can we predict excess heat? And there are some unexpected results that we'll talk about as well. This is the model output, the first page of the model output for Miley's calibration analysis against Miley's data. The left-hand side contains equations, and these are nuclear equations that involve one or two of the initial isotopes in Miley's electrode, plus 1 to 4, between 1 and 4 neutrons. It produces an initial fission product, and the initial fusion energy for those products is shown here in ascending order. So I've rearranged everything. I've taken 13,000 or 1,300 nuclear reactions that are possible in Miley's electrode, and now I've arranged them reduce the dimensionality of this problem, to get it down to something sensible. And so maybe it's the first 100 or first 200 that I'll have to be concerned with. And we'll take a look at these in more detail in just a second. First, let's look at the reactions. This one reaction that we're looking at here, this is vanadium 51 and iron 54 plus 3 neutrons, giving us indium 108. Indium 108 can undergo LAMP decay, okay, which is the normal decay processes for indium 108. And of the possible final stable products, the one that is selected is cadmium 108. And cadmium 108, it's listed in the isotope tables as theoretically possible of beta plus decay to palladium 108. First, I didn't include these, but as I started including them, I started getting much better resolution of my calculations and Miley's data. And then that's followed by palladium 108 is theoretically possible, theoretically capable of spontaneous fission. Okay, again, this is out of the isotope tables. And it produces 54 chromium. So what we've got here is we've got our energy, we've got our equations all ordered by increasing energy. Okay. And I'm printing out the energy balance. So given the equation, I can calculate what kind of fusion energy is required to cause the fusion. Then I run the model and determine the energy change due to the least action nuclear decay, rare decay, fission. I list the total and the total, the products of the reaction. So in this particular case here, we've got palladium 108 going to 254 chromiums. The Y's here indicate that it matches the Miley data on a 10 record running average, and also on a, I'm taking a continuous tally of where the matches occur. It's a pretty good match. I mean, we're doing very well here. But let's go further. There are some reactions that just cannot take place, and we have to just ignore them. For instance, the negative energy here is not permissible, so a silver 109 stays a silver 109. The things I've circled are new isotopes in this electrode. These are things, so what I'm saying is the first things that Miley saw in his electrode, although he didn't really measure them, was cobalt 59 and then manganese 55. And he measured that in several places. But the thing I want you to notice here, because it's very important, is see all of these isotopes that are already in Miley's electrode that are being created in this process? There's a lot of recycle. And what I'm seeing at the beginning of this particular simulation is a recycle rate of about 66%. That changes as you go through it. But there's an enormous amount of recycle back into the materials that were originally in Miley's electrode. And I also want to point out the excess heat here. If I take the average of this column here, I've got 0.0144 atomic mass units, and that calculates in this system to 2.69 watts. Miley reported 2 to 4 watts in his experiments. So we're able to get a pretty good handle on the heat. So what's Miley's electrode telling us? Miley has an electrode with 1,000 nickel-coated beads, and it is a single 1,000 bead electrode. It's producing 2 to 4 watts. The length of his experiments is about 12 days. And what I want you to understand is that the LAMP process here is a strictly sequential process. In other words, step 1 has to occur, and then step 2 occurs, then step 3. There's no cascade, okay? So it's a strictly sequential process. And if it is a strictly sequential process, how do you amplify heat? Well, the way you amplify heat is by taking his 1,000 bead electrode and creating from it 1,000 single bead electrodes, which would then produce 2 to 4 kilowatts, but you'd only have the reactions going for, I've calculated, about a half hour. I want you to think about this in terms of Rossi's experiment. Remember Rossi's, his shelves there with all of his reactors on them? Rossi had unknowingly discovered this. He was putting a lot of independent reactors in parallel and increasing the amount of energy that you get out of them. I have some ideas on how one might design a reactor like this. Well, what other experiments should we be doing? The other experiment, and this is the theorist in me, okay? The theorist has to always have experiments. If you don't have experiments, you haven't done your job. I'd like to take a look at the first couple of reactions that occur in Miley's electrode, or in some other electrode. So the best way to do that, I figured, is to take 99.9% nickel 58, a single isotope. This is available, readily available in the United States from American Element. Alloy it with 99.999% pure, one of the monoisotopic elements, scandium or arsenic, for example. And then do frequent sampling. In the proposal I wrote on this, we were doing sampling. We did an initial run where we had very frequent sampling, so we knew exactly when the first isotope was going to appear. And we take a look at new isotope appearance and the order of new isotope appearance. And these should check against the calculations by the LAMP model. Do you see what we're doing here? We're trying to take a look at the process, down at the nitty-gritties of it. You know, what are the first few things? If you go any farther into the process, there's a myriad of new isotopes, and it makes no sense whatsoever. That's what I was faced with when I started with the whole thing. These are the results for the first analysis of Miley's data that I completed, which is I used either rare decay or fission. Actually, I had only done the calculations for the rare decay, so I did that and I produced this. And I added then, when I got the fission only for the reactions where there was no rare decay. And what you see here is quite remarkable. You're reproducing Miley's data, okay, percent match, about 70 to 95, 96%. And when you get out here to 47 MeV, everything falls apart. And the reason it's falling apart is that's where Miley's experiment ended. And any calculations that I'm making beyond that are garbage. They won't match anything that Miley did. There's 3 regions on this plot. There's the excess heat operating range, where most of what's happening is producing positive excess heat rather than negative excess heat. Then there is the declining heat range, where the excess heat is tailing off and we're getting more of the negative excess heat. And finally, there is the no heat range, which is where we don't want to operate. So what you'd like to be doing is you'd like to be designing a system. Incidentally, going in this direction here, you're going to increasing fusion energy in step 1. What you'd like to do is you'd like to work here and maybe dribble a little bit into there, but you don't want to be out here because you're spinning a lot of wheels and you're not producing a lot of heat, if you want to produce heat. So let's take a look at what I did next. So here's the either rare decay or fission, about 70 to 100% resolution of Miley's data. But when I do both rare decay and fission reactions, everything sits at about 100%. It's matching Miley's data exactly. The outliers are germanium-70. There's 6 of them here, 7 of them. And also, selenium-78 is already beyond that. Lanthanum-139. I think that the germanium-70 is actually the zinc-70 that is in Miley's initial electrode and in his final electrode. And I think that his SIMS analysis is not sensitive enough to separate between germanium-70 and zinc 70. But take a look. I want to show you what's theoretically possible. I mean, this is the upper limit of what you could do with cold fusion. Okay. If I take the just on the basis of the nuclear performance, the nuclear coefficient of performance for the first record up there, the amount out versus divided by the amount in, I'm seeing about 73. So theoretically, you could get something on the order of a COP of 73, okay? And it depends on what kind of impurities you have in your nickel or palladium electrode or whatever it is. Well, let's go on. And this is a plot that David Nagel is always very fond of showing to show how confusing the data is in cold fusion. And I analyzed it using Miley's data. In fact, all of this is Miley's data. This is 6 of Miley's experiments. What I wanted to show you is that all of the initial elements in Miley's data were in this range of 50 to 70 exactly. None of them went outside of that range as an atomic mass number. And then he had, except for silver, he had silver 107 and silver 109. So what struck me so, what I've been so confused by in this plot for years is, why do you get the highest productivity? These are atoms per centimeter cubed per second produced. Why do you get the maximum produced where you have the original? I would expect that this would be a negative production and you get positive productions on both sides. The model told me why. Because of the recycle. Remember the recycle that we had? Where we were producing exactly what Miley had in his electrode originally. And when I take that and restructure Miley's, I take David Nagel's plot and I've cleaned it up a little bit, and I want to show you what the model produces, if the thing will work. The less mislaid plans of my voice and men. This plot, when it finally comes up, shows the Miley plot, the Miley experimental data up here. And this is the range in his initial electrode. And this is my first run. In this LAMP model, I have what's called an amend command. So after I get finished doing a run, there's a number of new isotopes that have been produced. I can then say amend, and it takes and it puts the newly produced isotopes back in the initial electrode and allows me to run it again. So on my first run with no amend, you see the 2 peaks here? One of them is at 50 to 70. The other is at, what do you get when you fuse those? 100 to 140. And what happens when you fuse those? You get 200 plus. What about going in the other direction? 50 to 70 goes down to 25 to 35. See where the peak is? And here's the 12 to 17 peak right through here. So the model is not only telling us something about the production of isotopes and the heat energy coming out, but it's explaining unusual performance of things like this. And I think what I'm going to do is I'm going to go to the end of the conclusions and just leave them here. The LAMP model seems to be doing a good job of producing the isotopes that Miley saw in his final electrode. It's the only theory that provides for the localization of energy within the electrode. It provides a mechanism for overcoming the Coulomb barrier. It predicts new isotopes in Miley's final electrode with better than 96% accuracy. It's actually up around 100%. Remember, absolutely deterministic. That's how physics should be. And the LAMP model verifies the 2 to 4 watts, that should be, that Miley measured in his experiments. The model calibrations approximate Miley's isotope production graphs. And if people want to either have my model or the data, I'm more than agreeable to any of that. You can talk to me and I can make arrangements for that. Or you can go to my book, which has all this material in it.
Okay, so good. Some question, somebody?
Theorists never get questions.
Okay.
Yes. I'm sorry.
I have a question. The model you are speaking about to produce fusion is based on that you have no dissipation processes in the system. But it's of course not true. You have a lot of dissipation, and you cannot, produce high energies that are enough high energies of the reacting nuclei to make fusion. Because if you want to fusion, let's say, heavy ions and overcome the Coulomb barrier, the temperature will be several billion degrees.
But it is.
No, there's not the case.
These are solar core temperatures or stellar temperatures.
Yeah, it was
and they're
result.
existing within, they're between the Mossbauer's nuclei. They can't be detected. A reversible thermodynamic process has the following characteristics. It has no entropy change, no energy change, and it cannot be detected because it has none of those things.
In the case of
other than through its work product. And
in the case of Mesmer effect, it's a very easy situation. You have an electromagnetic field reacting with the nuclei that are in this field. This is similar to the laser system that you have pumping and decay system. So there's a kind of enforced decay, gamma decay. This is a completely different situation, so you cannot compare.
Well,
but this, my comment for the first part of another one, I would like to ask you, you have calculated different abundances of isotopes, chemical elements. Have you compared it with the usual abundances that we have on the Earth or in our solar system? Because there is similar to that you have. It is usually neutron S process, capture process, that is responsible for the abundance of the heavy elements that, and is connected to the binding energy of neutron and different things. So I don't know, but this may be an indication that can be tested, that you compare your results with the known abundances of the isotopes or elements on the Earth. Okay, so it doesn't, and it is something that may be very important for any transmutation experiments, because you think that you produce new elements, but that can be simple enhanced diffusion inside the bulk of the material you have studied.
Yeah.
Okay, so there are different competitive processes that should be taken into account.
But all of these are the normal decay processes. Okay,
Yeah,
I'm not doing anything different here.
If you study S process, neutron capture process in stars, that's just what you said here. You have produced some heavy elements because of neutron capture, and they decay slowly in different chains, okay?
Yeah. The reversible process is one in which there is no entropy change and no energy change, but only the initial and the final products are operative. I reference Max Planck, his 1909 lectures at Columbia University. The first and the 7th chapter go through reversible processes and the principle of least action. I can't give you a better reference than that. The man is brilliant.
Okay, I think we can continue privately because time is going. Some other question?
Actually, I've got lots of questions. In one of the earlier slides, you had a two-dimensional diagram of the competing beta and alpha decays of dysprosium, I think. But
Yes.
you didn't actually show that any of those decays was the least action because there was no energy present in your diagram.
There was no
You didn't cite the energy of the competing beta and alpha decays.
those are all calculated into
I understand they're calculated.
smallest mass energy change. I'm
But
calculating.
you need to demonstrate that the smallest mass energy change was actually the path taken by these decays. Because the decays are well documented in the literature.
I do that in my book,
Okay, fair
which
enough.
you can see, because there I go through the details of exactly that calculation.
Okay, next question was, you said palladium 108 could fission, and I agree with you, it's energetically feasible. However, the Coulomb barrier is so high for the separation of the daughter products that the chance of it happening is extremely remote.
Well, you're at odds with the physics community there, because the isotope tables say that palladium 108 is theoretically capable of spontaneous fission.
I've just
And
said that.
I went through the energetics, and
I've just
in
said-
my
I agree with you,
calculations,
I agree with you.
Okay,
The problem is not the energetics.
it won't happen though. It doesn't happen in our world.
It doesn't happen, no.
Yes, it does not happen.
Okay, great. And
That doesn't mean it can't happen.
it does. The probability of fission is well calculated by the gamma factor for the separation of charged particles.
Okay. Yes.
Because you have an energetic barrier which you have to tunnel through, and this is the way you calculate the probability of fission, and you can calculate every individual daughter to see whether it's more probable or less probable than another. Energy itself is not sufficient. I think Konrad Chesky was saying exactly this earlier.
Well, there has to be a positive energy change in the
course,
fission
of
reaction,
course.
because it's an entropic reaction, and that's what I'm checking. I'm checking that,
Yeah, but
first
that's-
of all, I'm
the
only
point-
considering.
The point is that it's not sufficient.
Okay, then this is why I'm trying to write something down, so that someone like you can pick it up and tell me exactly what's wrong with it.
Okay. And regarding the zero entropy change, when a particular excited nucleus emits gamma ray, we don't know where it's going to be absorbed in the target material, and consequently there's an increase in entropy. It's more disordered because we've lost information.
You're missing one point. Let me explain it in a slightly different way. This is exactly the same thing that you see in a covalent bond, where you're sharing energy between two electrons. And I don't think there's any dispute that there's no energy lost between those electrons in time. Yeah, there's no entropy change
Okay,
in the
think,
covalent bond.
Sorry, but at the time is
This paper is about some foresight for the future development of different types of hydrogen metal energy sources. Because, in this project, the project is called HME, not to speak about nuclear energy. Professor Iwamura, for exactly more or less the same reason as you. So, what is this afternoon an HME heat source? This is a black box. You see a black box, and we have an excitation to supply some electricity in, and you get heat out. I will explain more about this kind of description tomorrow. For the moment, the problem is, supposing it works, what can we do with it? And I am on the industrial side of this project to try out what we could do with your inventions. So what are the uses of heat that could benefit from this kind of device? And this is a study included, indeed, in this project. So the first part of the study, this is what I am going to present this afternoon, only that. This is to have a look at the present uses of energy. So I'm not talking about the future and the implementation of energy, HME sources, but how is energy used in the world for the moment, before we introduce our systems. So if we look at sources of energy, of heat, You know, you have a source of energy. Oh, sorry. This is the wrong button, okay. It gives you heat and you use the heat. Easy. And these reactors in the future may displace combustion of fossil fuels, hopefully, nuclear reactors, solar collectors, excuse me, electrical heating, yes, thank you. And indeed, when you look at that, because we just provide heat, it may displace the heat used directly for heating purposes, for example, but it may also displace heat used indirectly, because at times the heat is converted into something else, and you use something else, not directly the heat. When you drive the car, you don't care about the heat in the cylinder of your engine, provided the car goes ahead. This is an indirect use. So an example of direct use, this is space heating, you know, metal melting, distillation, and things like that. An example of indirect use, this is again mobility. When you use an internal combustion engine, if you use metallic goods, it went through a metal foundry, melt at high temperature. When you use electricity, there is a steam turbine that was heated up, etc. And direct or indirect use, this depends on the point of view, of course. If you look at this steam turbine engineer, he is very much interested into the heat going to the boiler to feed the turbine, but you don't care about that when you use wind electricity. I say that because, indeed, we are obliged to have a look in this study at both direct and indirect uses of heat, because HME can supply both of them. So, let's go. What we want to know is the type of uses of this heat, direct and indirect, the number of users in the world, the different temperature levels, the different power levels, everything. And we had to look at some sources of information, you know, statistics from European, from America, national bodies, from professional organizations, the literature, well. And the more you look at it, the more you see that no source gives you the information you require directly. And indeed, it's even worse because different people use different frames to define the same industry. So at times it's difficult to find out what you are talking about. And for example, in Europe, you have statistics for Europe 28, and now you have statistics for Europe 27. And because of the Brexit, and you have to arrange your numbers. And of course, the COVID situation complicates the system because there was a turn down in 21 and 22. The reference date should rather be 29 or 20. Some difficulties, you know, some statistical data, a lot of statistical data. You'll find a lot about consumption of fossil fuels, CO2 emissions, okay, but it doesn't give you what you want. And indeed, to go fast, when you look at residential and commercial sectors, you know, you find also information, but this is meaningful only in OECD countries, not elsewhere. And another headache are the different units. You know, you have to find the translation between quadrillion BTUs, hexajoule, petajoule, million tons of equivalent, megawatt hours, and such things. You know, it's a pleasure. It's not the end of it, because if you look at the iron and steel industry, you have blast furnaces. You know, in the world, how much coal and coke goes into these blast furnaces. But all this carbon, this is not energy, because you need some carbon to reduce the iron ore. So you should not count it as energy, Because even if you imagine a blast furnace heated by an electrical system, you will still need carbon to get rid of the oxygen. And another example, in the aluminum industry, you produce the alumina at two different temperatures. You know, first in the Bayer system, you leach the bauxite at 150 degrees C, and after that, this alumina, you fire it at 1200 degrees C. So if you don't care about this, you find different strange numbers. And also in power stations, you have to make sure if you look at the heat input or the electricity output. These are, again, of course, different things. So it was necessary to simplify the data and to make extrapolations to translate regional data, for example, from Europe or USA into world data. And it was necessary to introduce average users for the different segments of this economy. And of course, it makes approximation, you know. And also the future trends, because everything is, the use of energy is increasing tremendously during the past years, except again for 2019. But this is not considered for the moment. So let's go. This is the kind of beauty you have to look at. You know, we are going to spend the next hour finding out what we want in it. And but to make things more clear, look for example at the residential use of energy. Fine. You find that by capita you use in Europe at least 15% of heat to heat up your water, 63 for space heating and things like that. And all in all, you find that each of us, we consume 6,400 kilowatt hours per year. It's a lot. But in America, this is 11,000. So how do you make an average of that, you know? Well, and in many countries, of course, it's much less. And in some countries, it's much, much less. So that's hard to do. Concerning the industry, there is something that helps, because most of the heat is used in what we call energy-intensive sectors, like iron and steel, like chemical industry, like mineral products, cement, to name it, food and paper. And some of us, you know, this is peanuts. And if you look at these energy-intensive industries, you count about 90% of the total. So I decided to neglect the 10% missing here. And this is what you get at the end after all these approximations, you know, for the different users, at what is the average power of each user. A domestic fridge, you know, 1 kilowatt. This is in megawatt thermal. For a light vehicle, maybe 100 kilowatt, and for an airplane, well, 70, and so forth. For the cement industry, we have some numbers for blast furnaces, cement. In some industries, they know exactly, especially in the energy-intensive industries, they know exactly how much they consume. And this is what you get. Here, this is a graph showing how many users you have according to the unit power at what temperature. So, of course, here we count refrigerators and water heaters, as well as nuclear power stations. So we count cats and elephants, goldfishes and whales together, one by one, but okay. It's a beginning. And because this is, again, a linear scale in this case, and you see that in terms of numbers, there are many, many cars, many, many residential appliances, and not so many industrial things. So to make things clear, let's introduce a logarithmic scale and you start to see something. But don't forget this is a logarithmic scale because here you have 1.4 billion automobiles running in the world and just 440 nuclear power stations, you know. So, of course, and all this is just an estimation. Of course, if you multiply the number of users by the power of this user, you get something else. You get the cumulated power in each segment, like this, fine. It seems to be much more even. You start to see the power stations. But if you show with a linear scale the number of cumulated power in terms of automobiles, refrigerators, water heaters, nuclear power stations, and things like that, you get this figure. It's incredible to see that this number of cars, you know, it goes up to the sky. Huh? This is just 10 million megawatt, and it should go up to 7.2. So, if you look, of course, these power stations, they run almost all the time, and the cars, you don't drive the car all the time. So if you look at the energy used, there is something much more, let's say, in accordance with what we may expect. Okay, now let's introduce some cold fusion or HME reactors in that. Provided we can supply heat at 100 degrees C, you can replace water heaters, you know, space heating, commercial heating, and things like that. That's good. If you are able to supply the heat at 350 degrees C, okay, you can supply all this food and beverage industry, even the Bayer process and some chemical boilers and things like this. That's fine. But if you can do it at 350 degrees C, you can start to imagine conversion into electricity generators. And of course, if you can produce electricity, you don't need these power stations anymore. And worse than that, if you have a lot of electricity, you can supply almost everything. So you know there is really a future for this kind of system, except that there might be a difficulty with mobility. Vehicles, cars, trucks, marine vessels, aircraft. In this case, we need the present technology using internal combustion engines and aircraft turbines, reactors. This is an indirect use, by the way, of heat, but they are energized, you know, they consume fossil fuels, and the fact is that they have a very high, fossil fuels offer a very high specific power. And how to replace that, you know, is really difficult, at least for the moment, I don't know. So, for the mobile equipment, it might be difficult to supply the heat we need for these moving things because of the necessity to have a high power density. But this mobile equipment may be satisfied by electricity, for example, to recharge your electric vehicle, or to supply hydrogen, or to make even synthetic fuels, you know, with hydrogen and CO2. Hydrogen, you know, I was in Mountain View a few weeks ago, and facing the place where I was staying, there was a power station, you know, from Chevron. And I saw these things, you know, said, what is this? I had a look at that, and indeed, this is a storage of hydrogen, liquid hydrogen. And this is the gas station, to refill your hydrogen vehicle with hydrogen. So it's going on. Hydrogen is not just a dream. And by the way, this is a Japanese company, Iwatani. Cheers. To sum up, there is an addressable market for sure for HME heat sources, you know. I don't want to detail this, but there are very large numbers of users in small power range, and also a small, 100,000, 10,000 number of users at much higher power levels. So for probably the prime market will be for residential applications, you know, heating, water heating, and things like that. Once we know how to make this, it will follow a learning curve, making it possible to deliver large heaters, you know. But of course, the big bingo will be to build these power generators, you know, because we are now talking in billions and billions of units. Next step, we have to evaluate development once we know exactly what your reactors will look like, you know, and what are the technological gaps between these, let's say, laboratory devices and the future industrial systems. And we have to consider also the ongoing energy transition and the competition of renewable energies. Yes, because we are not alone in this world, you know. And we all think here that we are going to supply cheap energy, abundant energy, eternal energy, easy energy. We all live in a paradise with dreams. Maybe at times nightmares as well, but also dreams. But now, you know, I'm sorry, I have to pronounce the end of our golden age and to come back down to earth, because indeed, the more we go, the more we have to realize that there are always several solutions to a problem, and a customer needs always to look at several solutions. And HME will be selected, provided it is better than other existing solutions. Don't believe we are in a virgin world. You know, this is not the case. We have to be better than others. An example of competition. You remember this picture, you take electricity, this is a black box, you get heat and you use the heat, that's fine. But the same scheme applies, exactly the same one for heat pumps. A heat pump, you have electricity, you take heat from the environment, and you get heat as well. So, even for space heating, we feel already that there will be a competition between HME reactors and heat pumps. And to show the fact, this is a picture from the European Union showing that they want in 2030 and beyond the number of heat pumps to increase. So, in other words, the European Union is financing us to go ahead, but they are also financing other things, you know, like renewable energies, heat pumps, and things like that. So, in conclusions, these HME heat sources may find a large use for space heating and water heating, with many, many units with low thermal power, and this is lovely in the industry. We love when we have to enter the market with small devices, because the initial ticket to build the prototype is very limited. It's easier to make a water heater rather than a nuclear power station. And if beyond that, you know that we will have to supply hundreds of millions of units, it's really a complete industry you can set up. The learning curve will give access to larger units, higher temperatures, and of course it will offer the development to large industrial boilers. Electricity generators will find applications all over the place. It's really the future, the dream to follow. Transportation might be more difficult because of the necessity to have high specific power, but it may be satisfied via indirect production of other fuels, like hydrogen, for example. And competition will exist, don't forget that. So that's all, thank you. To be followed next year.
So, excellent paper, make us the reality, and I agree most of your consideration. Most, not all, most. So, some people want to make question? Nobody. What happened? Oh, one. Japanese practical.
I have a comment on the competition with heat pump. We analyze the heat pump is superior under a low temperature. So, but if we use higher temperature, more than 300 degrees centigrade, we will win, I think.
Excellent, but this is the point. Some of the heat pumps, you don't even try to compete with them. Some others, you know you are the winner. So we will have to select our targets, you know,
That's right.
because we are not going to win in every case, but we have to be selective in the applications where we have an edge. Yes, for
Thank
sure.
you, thank you.
Thank you.
Please, the way.
Well, if you look at solar panels, you have free electricity, but then you have to pay for installation. So the initial cost will be part of the agenda, actually.
This is the problem with all renewable energies. The energy is free. No, the resource is free, but the energy cost because of the financial burden for installation, you know. This is true for solar collectors, wind turbines, all these renewable energies. It's true. And also, but concerning solar collectors, they work less in winter time and they don't work at night. So we might also have an edge, you know, in some cases.
Jacques, do you have any information source for EV charging in Europe, specifically by country, what the prediction is for the next 10 years on charging the increasing load of EV battery-operated cars? And also, I'm looking for data on what percentage in each country, if there is data, what percentage of their grid will be used to charge electrical vehicles? Have you seen any of that data anywhere?
Yes, this data does exist, but I don't have it in mind. And, well, I didn't have a look at this for the moment, you know, because we were just looking at the number of users in broad terms. Now, of course, for the continuation, we will have to make, to be more precise and to answer exactly these questions, yes.
Yeah, the numbers are huge in terms of what's required if 25% convert to electrical vehicles. In the US, the grid cannot support it, and it's just ridiculous how much electricity we need. So we need efficiency, we need new power sources, we need grid efficiency. There's a lot of work to do.
Just for electrical vehicles in France, if we follow this path, we will have to build 10 new nuclear reactors. Just for that. Okay. It's hard to make one. If we need 10, we have to do it progressively. Also, something important in the energy sector, you know, when you install some energy system, you have to consider the average duration is 40 years. When you build something in general, this is for 40 years. Coal firing station, this is for 40 years. Huh? The nuclear power stations, hopefully more. And so forth. Yes, yes. So the progressivity is something that helps, you know. Of course, we are not going to make a transition overnight. And when the politicians say, oh, we are going to change the world, sure, they never say how fast it's going to be.
Thank you for a wonderful presentation. I wanted to ask, though, if I could, we could go to a different place. Murphy's Law exists, and things always go wrong. What are the downsides on this? What could possibly happen that could tie this up? For instance, there isn't an LENR solution. What is it that can change your projections in disruptive ways?
Sorry.
Qu'est-ce qu'il faudrait faire d'autre?
Either, it could be government, it could be anything.
Yes. If you look it, to answer your question, it's enough to look at these national bodies, or DOE, or European, or international agency, energy agency. They have roadmaps, to develop what? To develop renewable energies. And at first, solar energy. But the sun, you don't have the sun day and night. So there is another roadmap to develop hydrogen production and hydrogen storage, and it's going on. So maybe the existence and the development of HME, well, it's the same, will put a brake on the development of solar energy. Probably not on hydrogen, because again, the cars will probably not run on HME reactors, but more on hydrogen in the future. And as long as we are not on the market, the development does continue with renewables. And nuclear energy as well now, nuclear power stations, yes. But
Okay, next question.
Jacques, do you believe that we are able to, cold fusion energy sources are able to compete?
Microphone, more.
Once again, so you are convinced about it that cold fusion-based nuclear or energy sources can compete to the large-scale reactors, gigawatt scale. What is important in this study that you should include also some construction materials needed for production of the energy. So in our case, we need a lot of, let's say, special metallic alloys. I don't know. Yeah, and in the case of large electrical power plants, you don't need so much. So therefore, there is. So I think at low scale we can be competitive to the other sources, but on the large scale, I don't know. What do you think?
I think that now, listening to you, understand that you left already this golden age, and you are down to the important questions. But maybe, looking at George, you may develop other systems using much less rare metals on fancy materials, Depends. We are not alone to develop LENR, Conrad. There are other systems to do it.
What about the potential for the knowledge within this group to facilitate normal nuclear and also thorium-based nuclear systems to remediate the waste?
Okay, so this is part of the next steps for next year.
Because
or
there are
2 years from
proven
now.
technologies in Japan and in Russia for these things.
We think we have to confirm these results. To confirm that, black and white, we know that it happens, we know that. There are a few papers of a few small organizations stating that. Fine. Now, if you want the governments to follow you, you have to demonstrate that, yes, it does work. Yes, you can expand this kind of remedial industry. Yes, you can do it. For the moment, we are not that far. This is the first step, but you have to go much further to convince people that it works.
And the barrier is that the people that are doing this research historically are either dead, nearly dead, or
They are people that are not access to radioactive material, and neither will they be granted because they don't have the right letters after their name. And they're not in the right institutions. So you need to bring together the parties that have demonstrated these historical processes with the parties that are able to provide the institutional cover to conduct the experiment, so that we then can offer these technologies that have been proven.
Absolutely. So, but once you want to touch at radioactive materials, you know, this is a completely different story. I remember in the past I used to work in the oil and gas industry. You know, I am going to tell a bit of my personal story. And my boss said, "Oh, we are going to talk to this nuclear power industry, explaining that when we make a project on budget and on time." I say, "Okay, try." You don't realize that in the nuclear industry, when you want to pour a base for a pilot, you have to fill up 2 or 3 kilograms of paper and get approval on that before doing it. Because this is the way the nuclear industry goes, you know.
So I think I've solved it. We have some Kerala sand, and we are going to we're sending some to parties that already have the technology. And so we should be able to replicate what was done in the 1980s and the 90s without asking anyone's permission and filling in any paperwork. So this will be published later this year or early next year, and we'll have done an end run around the brick walls.
And you have to make sure these papers are read by the correct people, you know. And that's a human problem. It might be the most difficult one.
There's a guy in India, and he created an Hho generator out of a waste plastic bottle and 10 rupees worth of razor blades, and it used a used hypodermic syringe. This produces the coherent matter, and he can go to the beach, get his own Kerala monazite sand, and conduct the experiment. So I know a lot of people in this area in Kerala, so it will be able to be replicated, and so I just wish institutions would have the foresight.
I do too. All of us, we do. But
sorry,
know,
maybe
administrations.
now. Sorry, but just a comment from the, if I can, we cannot forget that up to now, the typical operating temperature of the reactor is between 600 and 900 Celsius. So we have some limits about high temperature production for practical use. So we have to consider this point.
Oh,
up to now. In the future will change. But the technology is about less than 1000 Celsius. Okay.
This is your problem, and when once you know exactly how your system works, I know what to do with it. That's all.
Okay, Jack.
Okay.
I would just like to add one comment, actually. I was talking to my good friend Hugh Price, who was in Mountain View recently, and he was talking to me about the adoption of commercial LENR. And I said, well, as I see it, the technology faced 2 main risks. The first one is that it doesn't work at all. The second one is that it works amazingly well. And I think you have to aim for somewhere in between there. Yeah.
It's not the end of the day, yeah?
No, very true. Thank you.
Sorry, now the next speaker, Professor Alexandrov from Canada University, Lakehead.
Hello, everybody. In the first, I would like to thank the organizers giving me opportunity to present this talk, which will contain experimental outcomes of 2 sets of experiments. All of them, they are based on constant ton, an interaction of deuterium with constant ton wire. So now, some preliminary published paper regarding this actual matter. It was published last year, but it pertains to results got in years 2017, 2018. They show, this paper actually show experimental outcomes showing that indeed low energy nuclear fusion reactions in solids can be performed and can have the corresponding experimental outcomes. However, the results reported here cannot be used directly for further development of eventual energy source because the amount of the released energy is low. And the amount of the released energy was low indeed because I used at that time a mixture between nitrogen gas and deuterium gas. It is not flammable mixture containing 4.5% deuterium, everything else is nitrogen. But indeed it shows opportunity to perform cold nuclear fusion reactions in certain solids. So now, the first replicable experiments with constant wire at 950 degrees C initial temperature. Why 950? Because initially I didn't know that at this temperature, the specimen will be destroyed. That's why. And generally speaking, we are going to see the corresponding pictures based on this experimental scheme here. No plasma is used despite my system has opportunity to have a plasma. In all of the experiments which I'm going to demonstrate today, no plasma was used. So now, regarding actually these first experiments, why I'm saying replicable? Because we did several experiments at this initial temperature, and in all of them, the outcomes were the same. Destroying of certain specimen and metal release. So now, the specimen contains constant wire coiled on alumina rod. Heated, something like that. Okay, heated by AC, simple AC supply coming from auto transformer variac. By optical spectrometer, initial temperature was able to be made to be determined based on Planck's law through this window. So this is actually the chamber. This is the thermocouple, but the thermocouple is not in use. Now, here we're having residual gas analyzer, and here we're having injection of deuterium gas having relatively high purity. Now, what happens here in this case? It was actually the view of certain specimen at this temperature. Again, there is no plasma, and the glow which is visible here comes from the heated specimen. Again, the temperature was about 950 degrees C. Now, what happens when actually the deuterium gas came? Momentary evaporation of the specimen along the alumina rod. And it happened in all performed experiments. So now, the relaxing part, I'm going to return a little bit back. One end of the specimen relaxes on the sample holder. It relaxes actually on a system including alumina disc and sapphire wafer in the center of the disc. What do we see? So this actually sapphire wafer goes here. You can see here a clear picture of the destroyed specimen. Similar like in the downing of the photography. Which means that indeed momentary evaporation has occurred of the constant wire. It shows that I don't know exactly the time, but indeed it was momentary evaporation, because getting this clear picture of the specimen here, unusual, shows that despite of the fact that we have significant vibrations in the system, the clear picture takes place, which means that the time for evaporation is less than 1 second. Despite that in the future I'm going to present the results, assuming that the evaporation takes place for 1 second. And you can see here copper release on the wafer, copper release here also. So now, let's comment the experimental outcomes. The evaporation of the metal occurred along the entire winner rod, which means that the evaporation affects the entire length of the constant wire specimen, and it cannot be considered to be a certain point only, which means that we don't have something pertaining to thermal shock or about something else. It goes along the entire wire. The next comment is, because the part of the constant specimen was evaporated momentary in all experiments, a conclusion that momentary increase of the temperature happened in order for the temperature of the evaporation of the specimen to be reached. So now, the mass of the metal release due to the momentary evaporation of the experiments was about 0.37, it means 37% of the mass of the entire constant wire. And the total momentary energy required for evaporation of the metal was at least about 3,600, more than 3,600 joules. If we consider the mass of the specimen, it means we have more than 2,500 watts per gram released. I'm talking about the released power. At the same time, the energy flowing in the constant specimen in all experiments due to electrical heating was 240 joules per second. Now, as I mentioned, I assume that the evaporation was for 1 second, but in fact it was for less than 1 second. In this case, the ratio between the released excess power, energy, and flowing the electrical heating energy is approximately 15 times. However, it is based on the assumption that we're having actually evaporation for 1 second. But in fact, it is less than 1 second, which means that in reality, it is greater than 15 times. Further, reasonable questions. Is it possible this energy to have a chemical origin? No. As a matter of fact, yes, there is a chemical release of the energy, but it's only 0.19 joule. How I determined this energy? Simply in consideration of the parasitic injected oxygen, and I assumed that this oxygen burned totally in the environment of deuterium, creating deuterium dioxide, and all of this energy is concentrated in the wire. Of course, it is not realistic. But let's assume it this way. In this way, it is actually 0.18 joules, which is actually almost 18,000 times more than the released energy. Is it possible that this energy to have electrical origin? No. Because the applied voltage remains unchanged during the break of the wire. And normally the electrical break occurs at a certain point of the specimen. As in this case, the metal deposition was along the entire rod and also on the ceramic support. The applied electrical power was 240 joules per second. It means more than 15 times less than the released power. Why do we have to consider metal evaporation? Can we consider only metal melting? No. Because actually no metal droplets was found everywhere. Only, and the view, if you remember actually the view of the evaporated metal along the alumina rod, it is exactly the metal deposition which normally takes place in the metal in the vacuum evaporators. So now, is it possible the breakup to be due to the thermal shock caused by the incoming deuterium gas? No, because in this case, the thermal shock will occur at a certain point only, not along the entire wire. So now, a reasonable conclusion. The released energy comes from cold nuclear fusion reactions in the constant specimen caused by the absorbed deuterium. Also, this conclusion is supported by significant density of the released excess energy. As I mentioned, actually, about 2,500 watts per gram. No, joules per gram was the released energy. Or, if somebody doesn't believe a cold nuclear fusion origin, this actually somebody must consider that we are having energy coming from a known origin. Okay? Further, no radiation, gamma rays and neutrons outside of the gas chamber was detected during the experiments. In the next experiments, I'm going to show the exact actually equipment which I used for monitoring of the radiation release. The other experiments.
Dimitar, maybe now we make a short coffee break, and after we continue again, because time limits organization.
Okay, fine. It's okay.
Sorry,
yes.
but...
It's okay, it's okay, it's okay.
Thank you.
To take a break now? Yeah, break now. Okay.
Break now and after, on time here, okay, please. 30 minutes maximum.
Please remember that after the next session, there will be also a poster session outside for the people that desire to see the posters.
We had our wire at about 300 or 400 degrees. It was lower, but what we did observe is every time we put fresh hydrogen in, outside of the reactor, we had a guy in the tube, and he went triple count, and then after about 3 minutes, he went back down.
You're talking about the concept of wire.
With Chelani's made wire.
Okay. The things are in this way. If you, you will get this effect because actually...
We did sometimes when we had a vacuum. Yes, but that was normal vacuum deposition. Yes. So what I would argue is the Russians have taken nickel. They take about 1 kilo. So they heat it to about 300, 400 degrees, and then they put the fresh hydrogen in, and they get a flash of radiation elsewhere. They call it strange radiation. It is basically a toroidal structure like this, okay, like a big donut, and it's a cluster of the hydrogen atoms, but something that comes